So welcome. Thank you for joining our challenge today. So our challenge is called Multi-Channel MR Image Reconstruction Challenge. The organizers are myself, Yusuf, Wallace, and Richard. We are all from the University of Calgary. We were a little bit worried whether internet connections were going to work or not, so we pre-recorded most of the presentations. So today, everything is going to be pre-recorded except for the results and the discussion. So that portion of the challenge is going to happen live. If you guys want to make a question during the presentation, you can just unmute your microphone and ask the question. Or you can use the chat box. So I ask Richard, Yusuf, and Wallace to keep checking the chat box to see if there are any questions. So some of the presentations, they were recorded in different devices. So you may need to adjust the volume when you are listening to different presentations. So either increase or decrease the volume. I think, I hope that we're going to be around 2 hours today, maybe a little bit longer, with presenting this workshop and discussing the results. So yeah, let's get started. So just some housekeeping items, like we were discussing before. People live in different time zones. I guess some people are not able to watch the workshop in their current time zone. So this presentation is being recorded and we're going to make it publicly available afterwards. If you have any questions later, please just contact me. I'll be glad to answer any questions that you have. We ask you to kindly please turn off your cameras and mute your microphones unless you want to speak. And in case of technical problems during the session, let's say my internet connection breaks, we're going to be posting updates in the challenge website. So I recommend that you guys open a tab in your web browsers and you go to the challenge website as well. I would also like to acknowledge some funding sources. So here is the Canadian Open Neuroscience platform. They paid for my fellowship, postdoctoral fellowship in the past 6 months. I'm also glad to inform that I was just bumped to assistant professor here at the University of Calgary. So I look forward to collaborate with you guys in the future. Also, NVIDIA donated a Titan vGPU to our group. Also, we have the support of Amazon Web Services. So some of the teams, I guess 3 of the teams that we were working with, they asked for resources. So we were able to provide computers in the Amazon cloud so they could train their models. Out of the 3 teams that use Amazon, just 2 were able to complete the submission. In fact, 15 teams registered for the workshop, but most of the registrations were before the COVID situation. And at the moment, we only have 3 complete submissions, but the challenge is going to keep going as an online challenge. So hopefully more people will submit. We also like to acknowledge the MIDL organization, in special Joel Kervadek and Pierre-Marc Jodin. They were instrumental in providing us the necessary resources to make this challenge become true. I would also like to acknowledge Dr. Cheryl McCreary and Dr. Louis Lozon from the University of Calgary. So they helped us with the data collection and how to save raw data directly from the scanner. And also Dr. Robert Mark Lebel from General Electric. He helped us to access the raw data. GE has a proprietary raw data format, so he helped us to access the data. From now on, the presentation is going to be a recorded presentation, but feel free to interrupt me and ask any questions. So this is the outline of our presentation today. 15 teams registered for the challenge, but only 3 of those teams were able to submit a solution in time. So today we have a few baseline models. So 5 baseline models. I'm going to go quickly through those, and the teams are going to present their proposed solutions. So we have ML Unicamp. This team comes from the University of Campinas. We have TU-MRI. I think they come from a university in Germany. And Resonance, I think they come from a university in the Netherlands. So I haven't had the time to watch the presentation, so I'm really excited to be able to see what they propose to solve this MRI reconstruction challenge. So I'm going to talk a little bit about the motivation for this challenge. So we know that MRI acquisition happens in K-space, so we collect samples in K-space, and if we follow the Nyquist theorem, we just apply the inverse Fourier transform, and we get an image that has a good quality. So see here, as we collect data in K-space, the quality of the image improves. The image resolution is determined by the maximum frequency that we sample in K-space, and the field of view is given by the space in between those samples. So when we follow the Nyquist sampling theorem, acquisition is slow. You have to acquire too many samples. Reconstruction is fast because it's just an inverse Fourier transform, and usually you get an image that is good as long as the subject being scanned is able to be still inside the scanner to avoid any motion artifacts. Usually MRI takes between 45 and 60 minutes. So for each exam, we usually acquire several sequences. We have an MRI protocol that has many sequences, and it can take up to 1 hour. So that's a very long exam. And this causes like many problems such as wait lists to get an MR done. The exam cost is also very expensive compared to other modalities. So reducing MRI scan times can bring several advantages. The number one is perhaps reducing MRI exam costs and wait times, potentially allowing the addition of more sequences in the MRI protocol so we can better characterize the region that we are investigating. It can also reduce motion artifacts because, well, scans will be shorter, so it'll be easier for the subjects to be still during the scan. Also, faster MRI can lead to higher image resolution. One of the drawbacks, which is not really a drawback, is that larger volumes of data will be available for radiologists to analyze. So we know we don't have many radiologists nowadays, and if they're talking about accelerating MRI by 10 times and maybe generating 10 times more data, we will certainly need more machine learning tools to go through these data sets to help radiologists to perform the analysis in a time-efficient manner. There are two techniques that are currently employed in clinics. So parallel imaging, which tries to leverage the spatial location that the different coils gives us, and also compressed sensing that tries to leverage image sparsity to sample K-space at rates lower than the Nyquist sampling theorem. So many of those techniques are potentially slow because many of the reconstruction algorithms are iterative, so you have to go on many times and you don't know how many times it will take to achieve a solution. Also, traditional PI and compressed sensing, they are used in the clinic, but still at very conservative acceleration rates, so it could potentially make MRI exams even faster. And deep learning-based reconstruction is considered a new frontier of machine learning. It has a few advantages. So it reconstructs the image in a single pass through a properly trained network. So it's going to be faster. You don't have to go through many iterations to get a reconstruction. Also, if you think about the cost of GPUs compared to the cost of the MRI scanner, it's really a small fraction of the cost. So it's potentially cheap to incorporate those in modern MRI scanners. The optimized GPU code allows for real-time reconstruction, and many preliminary works have shown that deep learning-based reconstruction outperform traditional parallel imaging and compressed sensing techniques. So I usually like to classify deep learning-based reconstruction into 4 separate groups. The first group is the image domain learning. So basically you have your sample K-space, you zero fill it, and then you apply the inverse Fourier transform. You get what is called the zero fill reconstruction at this stage here, and then it goes through a deep learning model that tries to reconstruct the image for you, or perhaps you could say enhance the quality of the image for you. Most of the techniques published so far, they fall under that category. You also have K-space domain learning. So in this case, you have your sample K-space and your deep learning model happens in the frequency domain. So basically you're trying to interpolate the missing positions in k-space, and then you just apply the inverse Fourier transform to get your reconstruction. The other two groups are domain transform learning. So in this case, you try to learn transform the maps directly from the sampled k-space to your reconstructed image. I guess the most famous technique that falls under that category is AutoMap. It was published in Nature 3 years ago, if I'm not mistaken. And the major drawback of the technique is that it can have potentially billions of parameters. So hardware is really a limitation here. And also the models are specific to an image size. So if you have an image size which is 256 by 256, you have one model. If you have another image that is 228 by 228, you need to train another model. So that's a drawback here. And finally, we have hybrid domain learning. So the idea here is to have a deep learning model in the frequency domain. Then you have a deep learning model also in the image domain. And connecting those two models, you have the inverse Fourier transform. In this case here, we don't learn the transform. We just use the mathematical equation that is already available to us. So it tries to leverage information as you see it both in k-space and image domain. And we know the information is the same because they're connected through a linear transformation, but the way that information is processed in each domain is different, so that can potentially lead to better reconstruction. Some deep learning based reconstructions, they have a few limitations. So one of those limitations is the lack of benchmarks to compare different models. If you go through many publications, they all use a different data set. Sometimes if you search for that data set, it's public, but then you discover that it's not a raw data set. It's a data set of reconstructed images. And while they don't really explain how do they go from reconstructed images back to k-space, how they simulate that. So benchmark data sets are essential to make the field move forward. FastMRI is a great initiative, but data corresponds mostly to two-dimensional acquisitions from the NID. I think now they also have acquisitions from the Brain 3D acquisitions. So it's a great initiative as well. Also some limitations. So many initial models were proof of concept models. They were tested on single channel data, which is not really realistic. Generalizability of those models is still a concern. It's something that we try to tackle here in this challenge. Also, how many models do we need to train? We need to have one model for each body part, one model for each different acceleration factor, one model for each coil configuration. So those are all questions that we still need to investigate further. And also, interpretability of those models is a concern. Sometimes we would like to understand better what is happening behind the curtains when you have a deep learning model doing the reconstruction for you. So the goals of the challenge here is to compare different deep learning-based MRREc reconstruction models on a large data set, which is composed mostly of 3D MRI acquisitions. And the second goal is to assess generalizability of the model. So here you're going to train your model using 12-channel data, and we want to see how well it generalizes to 32-channel data. So now Wallace is going to present the challenge description for you guys.
Thank you, Roberto. I'm Wallace, and now we're going to talk about the challenge description. This is our category convenience dataset. We have two different paths, a segmentation and a reconstruction. In this segmentation, we have 359 tier 1 images from different vendors, Philips, Siemens, General Electric, and we also have different magnetic fields, 1.5 Tesla and 3 Tesla. We also provide brain, white matter, and hippocampus segmentation masks. In the reconstruction path, we provide the raw data from the single channel and the multi-channel. So far, we have 495 downloads over more than 40 institutions across the globe. And here is our web page where you can find this information as well. Here is our description of the dataset of the reconstruction path. We have 3D T1 sagittal acquisitions, images collected as a part of the Calgary normative study. We are using a GE scanner. Our subjects on average are 44.5 years and a standard deviation 15.5 years in a range from 20 years to 80 years. We are using two different acquisition parameters, and we are collecting only 85% of the K data, and these are taking around 341 seconds. Difference between 2D acquisition and 3D acquisition is when you're working in a 2D acquisition, you have the phase encode and the frequency encode, and then you're here, you can do only 1D sampling. But when you're working with a 3D acquisition, you have the phase encode and the slice encode. And now we can do a 2D sampling. And when you're applying the inverse Fourier transform in the frequency encode direction, you're going to reduce this from a 3D reconstruction to a 2D reconstruction problem. And this is how we are splitting our data set. We're splitting according to the number of coils. We have first 7 images for training, and the number of slices is 12,032, and the public 20 images for validations and 5,120 slices, and also public for 50 images for test, and the number of slices 12,800, and it's not public. From 32 channel, we have 50 images for test, and the number of slides 12,800, and it's also not public. And one file, one 12 channel file, has around 0.95 gigabytes, and a 32 channel P file has around 2.5 gigabytes, and a P file is a format of the GE data. This is an example of a 12 channel data. We have 12 K spaces here, and we're collecting 85% of the K space. Then you can see this black stripe here is the part that we're not collecting. And then we compute the inverse of the Fourier transform, and you're going to have your 12 images here, and you're combine them, use the computing the root sum of square, and then you're going to have your final image. Similar, we have an example of 32 channel now. We have now 32 K spaces where you're going to compute the inverse of the Fourier transform. Then you will have 32 images, and we're going to combine them and use the root sum of squares, and now you have your final image. And how can you assess the data? First, you need to complete the Google form, and when you complete it, you will receive a link by mail where you can make the downloads of datasets on G Drive or OneDrive or Amazon. The data is anonymized and saved in ATF5 format. You will also receive a spreadsheet with relevant acquisition information, and you can also find in our GitHub information about how to load the data and how the metrics going to be computed in the challenge and other information. So feel free to access our GitHub as well. Here is an example of email that you will receive, and you can see here links from G Drive or OneDrive where you can download the entire dataset, and also links from the Amazon where you have different parts and you can click and go and download it.
I think we have a question about the 85% of sample data. I think it's from Nathan Ken. I think Louis is our physicist. He's in the session. Do you want to answer this question? So he said that for 85% sample data, he expected this acquisition to be longer. I'm sorry, I'm not an expert in my acquisition, but Louis, our expert, I thought he was connected to the session. I'm not sure.
Yeah, sorry, Roberto, I am connected. So the scan time is still about 6 minutes. So it's a 3D sagittal. And yes, the reason we take 85% is to reduce. We typically like clinically to get down to about 5 minutes scan time. So an 85% KZ sampling was sort of a good compromise to get to something that is clinically valuable. It's still a fairly long time. So that's the reason. Does that answer your question?
Yeah, so indeed. So I think you found a really nice trade-off here. So yeah, that's yeah, congratulations, well done.
So it's Richard. I think there might be one other difference. We're using the G implementation, so it's a Bravo sequence, as they called it. I think the TI times are actually different than, say, the Siemens or the Philips implementation. Louis might be able to comment more on that. You're muted, Louis, if you're trying to talk.
Yeah, so the Bravo is basically an inversion recovery FSPGR. So the way the Siemens does it, their inversion, they collect multiple KZ as it goes through. As Richard is saying, it's a slightly different implementation, but by and large, even on a Siemens platform, I think it would be 5 to 7 minute scan time. So it's the equivalent of an MP-RAGE, just done in a slightly different fashion, that's all.
Thank you.
Thank you, Louis, for answering that. Let's keep going.
Different parts of the data set, and also from the test and the acquisition parameters here as well. Code of conduct. So we have some rules in this game, and we expect that all members follow them. And the first rule is honesty. So we expect that all team members shall act honestly with integrity and competence to achieve the goals of the challenge. Rule number 2, no misconduct is allowed. All team members shall not engage in any conduct involving dishonesty, fraud, deceit, or misrepresentation seeking to influence the results of the challenge. Rule number 3, respect. So we respect that all team members will act with courtesy and professional respect towards the organizers of the challenge and members of the other teams participating of the challenge. So here is an example how not to do. So we have simple mask for 2 different acceleration factors. Someone could just merge them, and then you're gonna have more samples from the gate space, and you can achieve better results using the acceleration factor 5, combine the results of the acceleration factor 10, and vice versa. And this is not nice. We have 2 different tracks. In the track 1, the sampling masks will be provided from 2 different acceleration factors, 5 and 10, and the submission will be evaluated only in the 2 out-channel test data. In the track 2, the sample mask will be provided as well, but your submissions will be evaluated on 12 and 32 channel tested data. The teams are going to submit the reconstruction using a predetermined template. The teams need to make your codes available, and no additional data for training is allowed. These are the metrics used in the challenge. We have the first one here is the structural similarity, where one represents two identical images. We also have the peak signal to noise ratio, where higher values are better. This first group here is a traditional metrics, and we have the visual information fidelity, where its high values are better. And this one here shown to have a strong correlation with the radiologist's opinion, as reported in this paper here. And the reference used to compute the metrics are the square roots of squares. And how the ranking is computed: first we sort the weighted average among the metrics, and for each metric they have different weights. So 0.4 for VIF, 0.4 for SIM, and 0.2 for PSNR. And here is an example. I suppose we have 3 teams. Here are the scores from the different metrics. Then we sort the first metric and multiply by the weight of the metric. Here the VIF has a 0.4, and the Good Boys was the 3rd position. The Code Bears 2, 2nd position, and Mr. Anderson 1st position. And then you multiply by the weight, and you do the same procedure to the other metrics. Here is the SIM. You have the position of the teams, then you multiply by the weight of the metric. You keep doing this to the last metric, the PSNR. You sort, and then you multiply by the weight of the metric, and then you will have the final score and the rank of teams.
That was the challenge description. Now we're going to move on to the models. So we're going to start with the baseline models, and then we're going to show the presentation for each team that submitted to the challenge. Thank you, Wallace. Now I'm going to present the baseline models, and each team has pre-recorded a video presentation of their submission. We have 2 processing strategies. So the first one is what we call the single channel configuration. So we train a network that processes each channel of the multi-channel data independently. So this way, this model can be applied to any number of coil channels. The second model is what we call the multi-channel configuration. So basically, we have a network that receives all channels at the same time, and reconstructs all channels at the same time as well. And we just combine those channels using root sum of squares. So in this case here, the model is specific to the number of channels that we have. Also, in the baseline models, all baseline models will split real and imaginary components of the complex values as separate array channels. We don't have the real complex value representation. We split those into separate channels to make things more manageable. And the first baseline model, it's very simple. It's just zero field reconstruction. So you have all your sampled case spaces as input. You take a channel-wise inverse Fourier transform. You get several images, and then you combine those using root sum of squares, and you get what is called the zero field reconstruction. So the zero field reconstruction is commonly used as a starting point for more complex reconstruction models. And the next model is just a UNet. So this model was actually published in 2017. So the authors published the use of a UNet for CT reconstruction, but they also say that it can be applied for MR reconstruction. So this is the architecture that we trained, the same as in the paper. So all the results that you submit here will be directly comparable to the UNet and published in this paper. The input is the channel-wise zero field reconstruction. The output is the channel-wise UNet reconstruction, and then you combine the results with sum of squares and you get your final reconstruction. So this model has approximately 32 million trainable parameters, and it was trained using a mean square error loss. The next model is the hybrid cascade. So this model we published last year at the same conference, so medical imaging with deep learning. And the idea is kind of cascading convolutional neural networks, but across different domains. So here, the input is the zero field reconstruction. Then it goes through an image domain convolutional neural network. We do the data consistency step. And then we have a convolutional neural network in K-space, data consistency, another convolutional neural network in image domain, data consistency, K-space, and in the end we have two image domain blocks, which gives us the output. So data consistency is just replacing the predictions of the network by the sampled values, the sampled K-space values. And there are actually many ways that you can do this, but we just use this simple approach. This model has approximately 1.2 million trainable parameters. The configuration is IK, IK, II. So we have 6 subnetworks. Each subnetwork is in a different domain, either image domain or K-space. We trained the model using a mean square error loss function. This is the architecture of each subnetwork in the model. So it's just a flat convolutional neural network. Each subnetwork has approximately 200,000 trainable parameters. And the next model is what we call the WWNet. So basically we call the WNet is the concatenation of 2 UNets. And since here we have the concatenation of 4 different UNets, we call this model the WWNet. And we start with the zero field reconstruction. We have a UNet, then a data consistency block, then a K-space domain UNet, data consistency, image domain UNet, and so on. So it's similar to the previous model, but we're using UNets, which have a higher capacity. The UNet that we use here has approximately 3 million parameters. And the configuration is this one, so image domain K-space, image domain K-space. And we also use a mean square error loss. And this model was also published this year, so all the results submitted here are directly comparable to this model as well. This is the UNet architecture that we use. So it's a smaller UNet compared to the UNet that we saw a few slides ago. It only has 3 million parameters, trainable parameters, this UNet. The next model is the parallel architecture. So in this case, the input here is the zero field sampled K-space. And we're going to have in parallel a K-space network and an image domain network. After each of these 2 networks, we have data consistency steps. We go back to image domain and we concatenate those results. And then we have a consensus convolutional neural network, which gives a channel-wise reconstruction. So this network here has approximately half a million trainable parameters. We also train using a mean square error loss. And this is the architecture that we use for each subnetwork. It's very similar to the hybrid cascade model. And each subnetwork has approximately 165,000 trainable parameters. And now let's move on to the submissions. Yeah, so let's move on to the submissions now. I would ask before I start playing the video for each team that if possible, if they are present here, that they introduce themselves so we can get to know you a little bit better. And the first team to present is, just one second. Yes, it's TU-MRREc. Are you guys present? Charus, Devendra, Fabian, Maik, and Victor?
Yes, hello.
Hi, can you introduce yourself? Just talk a little bit about your team and your motivation, what you're working with MR reconstruction, or if you just like participating on challenges?
Yeah, sure. We are from a university from Germany, from Munich, the Technical University of Munich. And we are participating in the challenge because we are right now doing a practical course on our university. And our instructor had the idea to take the subject as the practical course subject. And while we're on it, we could also, it was free for us to participate in the challenge. So it was our decision. And so we decided to do it and see where we are going with it. And also while I'm at it, I would like to thank you again for giving us a possibility to train on the Amazon Web Cloud service, because we had problems with the Google Cloud. And so it actually helped us a lot to finally train our models. So again, thank you for that.
No worries. I'm glad you were able to submit to the challenge. So I'm gonna play your video now.
Hello, I will present to you the approaches of my team for the multi-channel MR image reconstruction challenge. Team members are Devendra, Fabian, Mike, that is me, Victor, and our supervisor is Dr. Shivers. Let's start with the clinical motivation. So MR imaging has some significant advantages and is a powerful medical image technique, but it also comes with a major drawback, which is the overall acquisition time. So a normal session lasts between 20 to 60 minutes, which is of course a high cost factor and also a high stress factor for the patient, because the patient must not move during the session to avoid motion artifacts. So it would be good to reduce this acquisition time. However, this comes with some problems. So what happens during a MRI session is that a case space is sampled, which then can be transformed via an inverse Fourier transformation to the actual image. And if we now increase the acquisition time, so we have a lower acquisition time, it comes with a undersampling because we are violating Nyquist sampling law. Therefore, we will then have an undersampled case space, which we can simulate by just applying this Poisson distributed mask to the original case space. And thus we sample about 20% of the image. And if we then apply the inverse Fourier transformation, we get an image like this. And as you can see, a doctor cannot really use this image for any diagnosis. Now the idea is to use a deep learning model that can transform this image, it can reconstruct this image to something like a ground truth. And this is what we tried. And now I will explain to you what exactly we did. First, we used a baseline model, which was published by Roberto Souza et al. And here we have consists of modified units, which have less convolutions than the original unit and less parameters, so about 3 million trainable parameters. We have the usual encoding path. We try to map the information to a submanifold in a lower dimension. And then we have our decoding path. We have some concatenations here, some skip connections where we concatenate the channels. And we have here the data consistency. This just ensures that we use all the originally sampled information of the case space of the image. So because this sampled information is of course true, this is correct, and we definitely want to use that. That is why we just apply it at the end to the output again. Now we can stack these unit blocks to a double unit or even to an even bigger network. And here we have to be careful that we again have the data consistency between those unit blocks. So here again we ensure that we use the original sampled case space.
these unit blocks can now work in different domains. So either they work with k-space, in the k-space domain, or they work in the image domain. And they can also work as a hybrid model. So one unit block is in the k-space domain, the other is in the image domain. As I said, this is the baseline model that we used, that we first implemented to have a kind of comparison. And then we thought about features that we could modify or things that we could add. We came up with 3 different things. First of all, we wanted to add skip connections between the corresponding unit blocks, which was kind of inspired by the dense net, where they have these dense blocks with lots of skip connections. The other thing is the loss function. In the original paper, they used a normalized root mean squared error. And here we wanted to try a differentiable width score as a loss function. The width score is visual information fidelity index. It's a measure that is very close to the human eye, to the perception of the human eye for image quality. So it has a close correlation, which is why we thought we could try this one as a loss function. And last but not least, we wanted to add complex convolutions because we are working with images that consist of a real and an imaginary part. And to use this correlation, we needed to use complex convolutions. Let's start with the complex part. So here you can see the modified unit. We now have complex convolutions where we have the real layers and the imaginary layers. We implemented the network in PyTorch, and there are no complex numbers possible. That's why we had to use the following approach, which was inspired by the paper cited at the bottom. Here we have our complex kernel, which consists of a real part and an imaginary part. And now we make use of the distributivity of convolutions, and thus we can rewrite this complex convolution as 4 convolutions. And this looks as following, and we can have it in matrix notation, which looks like this. And so we just use 4 different convolutions without having the need for actual complex numbers in PyTorch. So we circumvent this problem by that. The other thing now is, as you can see here, we have the yellow layers are the max pooling. And max pooling wasn't mentioned in this paper. So we tried an idea where we just calculate the maximum, the absolute of the complex numbers like this. So we just square them and take the square root, which is basically the length of the vector if we consider the complex number in this Cartesian coordinate system. And thus we have, again, the maximum, we sample the neuron with the highest absolute complex number. So the other modification now is the dense part. So we added skip connections that you can see here. Now we don't only have the skip connections in between those unit blocks, but also from one unit block to the other. And as I said, it was inspired by the dense net. Here we have to be careful that these unit blocks now need to be in the same domain. So it makes no sense to have skip connections when one unit block works in k-space domain, and then we have this data transfer where we transfer k-space information to a unit block that is working in image domain. So here we have to see that we have the data consistency. And as a last modification, we introduced a new loss function, the width loss function. As I said, the width is a visual information fidelity index, which which assesses image quality, and it is deemed to be very close to the perceptual human eye. So there's a high correlation, and also the width function was used as a metric for the challenge. So that's why we thought that it might be a good idea to use it as an actual loss function. And here is how we applied it. So of course, you cannot apply it directly to the complex numbers, which is why, again, we took the absolutes of the numbers for each of the 12 channels. And then we summed up the width loss over these 12 channels. So therefore, we created this loss width. And now we took a weighted loss of the width loss and L1 loss, which you can see here. And this is due to the fact that this L1 loss ensures that our data range is on the track with the data range of the ground truth. Because if the data ranges would now differ tremendously, then the L1 loss would punish that and ensures that we are kinda at the same data range. Here you can see our results. The unit baseline numbers are from the challenge webpage, and here are the numbers of our network, which are taken on the validation set. I think the unit baseline is taken on the test set, so we cannot directly compare it, but we have a certain tendency here. We can see that especially the width score is very decent, and I think this is mainly due to the fact that the width score is actually the loss function that we are training our network on, so it makes sense that this is quite good here. At the bottom, you can see an example also from the validation set. So we have our ground truth, we have our undersampled input that we feed to the network, and then we have our prediction. And the prediction is so far not too bad, but we can also see that it's not perfect yet, especially the fine features are not modeled correctly. So here we have very detailed features in there in the ground truth that are yet missing in the prediction, and we need further tweaking there. We've trained it for 35 epochs and have not yet, we think that it has not yet overfitted, so there's still room for improvement. And we could also increase the number of units that we stack together. This one is just 2 units stacked, and we could also use 3 or even 4. And then we will have to see whether this makes for an improvement or not. So this is for the future work. Now, if you have any questions, we will be happy to answer.
Thank you for the nice presentation. I guess we have a few minutes for questions in case anybody has a question for the team TU-MRREc. I'm going to start with a question here. So I think it's a great idea to have a complex value neural network. Congratulations on that. I've seen a few papers even on MR reconstruction. I think they implemented a complex value UNet against a UNet that splits real and imaginary, and they show that the training works better. So congratulations. I think that's a very good idea. I don't think, at least I don't remember, but did you explain how does the activation works with complex value numbers?
What do you mean by activation?
So usually after each convolutional layer, you have an activation, either a rel.
Yeah, okay. There were actually different functions mentioned in the paper. So they used a complex value activation function and a cardioid function, something like that. But in the end, they found out that the vanilla value, so the normal value as always, worked the best. So they couldn't really explain it as far as I know, but the plain value activation function worked the best, so we went for that.
Thank you. Any other questions?
So maybe a practical question. So you went quite far in optimizing the network architecture. So how did you go practically about this? Because, you know, training on this large data set is not a small effort. So how did you do this, like practically?
So the reason why we stick to that, actually we tried different architectures. This WNet was the first architecture proposed by our instructor. And we had a architecture about reinforcement learning, which didn't work out too well. And as we only started in May, I think, we decided in June to just go with the WNet architecture. And the training was basically, I have a GTX 1050 graphics card, and I tried some different parameters, and there we could see where we're going if the direction is correct. But we didn't do too much training because we never really had access to powerful GPUs. So actually, we don't really know whether we are perfect right now or whether there are, so most likely we're not perfect, but whether we're on the right track, because we didn't test too many things. We just either got lucky or it's in a mediocre result that we submitted. But we didn't train actually for very long. And in the end, our biggest architectures were a quadruple unit, and they took about 30 hours for 30 to 50 epochs, something in between. And so we had some days for training and just went in for one architecture.
I have a question, if I may. Very nice work, Mike. I'm just wondering, the prediction that you showed, especially in the brain, it was kind of smooth. I was wondering, is that smoothing due to the inherent undersampling, or is it due to the loss function? And how do you hope to correct that?
So we don't really know why it's so smooth, because well, first we went for a weighted loss function, but it was L1 and not mean squared error. So that should rather speak against the smoothness. And if we have just a width loss function, I've tried to train it on just one sample, and there was no real smoothness. So in the end, it had very sharp features. So it's not inherently in the loss function, but either it isn't trained long enough, or the network was too small, or there is actually some part in the loss function. It's difficult to say, and this is actually one aspect that we are still trying to figure out. We still have to improve.
Thank you.
Oh, I want to add something. I want to thank you at the beginning from the organizers because of this great challenge. And I think that our team here has done lots of good things, because they were, as Mike mentioned, they were started about 1 month ago around that. And so they try to adapt themselves to the field and be more familiar. So they have tried some things. About the question that you mentioned, yeah, I think that this smoothness is somehow related to some part of the loss function that we have used, and we have a bunch of ideas to implement. And of course, because of the limited resource and the high computational complexity, so we should try it in the next weeks, hopefully. Anyway, we would try to bring some other ideas from the patches of the images extracted from there, and then extracting some other information from other loss functions that help us to increase the information that we have in the images. I think this smoothness is some parts would be related to the nature of the loss functions that we have, but we would see by examining the other loss functions or maybe the other structures. Thank you.
Thank you for the great presentation. We're gonna move on. During the discussion session, I have a question that is gonna go back to this presentation related to the VIF metric, but I'm gonna reserve that just for the discussion session. So the next team to present is the ML Unicamp. So I guess Livia and Alexandre, if you guys are online, if you'd like to introduce yourselves before I play your video.
Hi, my name is Livia. I'm here. Alexandre is here also, actually, but we're here representing our team. We would like to thank you, Roberto, and the organization. This was really challenging for us. That's the first time we work with reconstruction, but it was really fun, actually. So thank you. I hope you like the presentation.
Thank you. I'm glad you guys were able to submit a solution. So let's see what you guys prepare for us.
Hi, my name is Livia Rodrigues. I'm here to present the ML Unicamp results in the multi-channel MRE image reconstructions challenge. Magnetic resonance image is the standard exam for monitoring brain structure and diagnose neurodisease. However, its acquisition time can exceed 30 minutes per subject. Currently, there are two main methods used to accelerate MRI time. At first, we can cite the parallel imaging method, which is the most used in clinics. Then, there's the compressed sense method, where images can be reconstructed from subaqueous sampling. However, this method can produce artifacts in the image. These methods are able to shorten the acquisition time. However, they can even increase the reconstruction time at a point that the reconstruction will only be finished after the patient leaves the table. So our main goal here is use the deep learning methods to help reduce the reconstruction time. In the literature, we have different types of reconstruction methods for deep learning. The image domain method processes only the image in the spatial domain, and the sensor domain method processes only the image in the k-space domain. The domain transform learning methods, on the other hand, has as inputs the k-space image and outputs a spatial domain image. The hybrid method is gonna use the image domain and the sensor domain methods together. So it's gonna have a cascade of modules, and each module is gonna process a different kind of image. Then there's the spatial domain or k-space domain. This challenge is composed by two tracks. In both of them, the organization provided us sampling pattern masks for R equals 5 or 10. In the first one, the submissions are evaluated on 12 channel test data, and in the second one, the submissions are evaluated in the 12 and 32 channel test data. The dataset is composed by 47 T1 weighted acquisition training images and 20 T1 weighted acquisitions for validation. Our team architecture is composed by 7 network modules in cascade. I'm going to show the full architecture in the next slide. Well, all you need to understand here is that each module is represented by a UNS-based architecture. The architecture is composed by 7 modules, represented here by the blue boxes. The Ks represent the modules that process the K-space images, and the Is represent the modules that are going to process the spatial domain images. In the first block, we have 2 modules in parallel. The first module is going to process the K-space image. The input is going to be a 24-channel image, and the output is also going to be a 24-channel image. The second module is going to process the spatial domain image. The input is going to be a 24-channel image, and the output is going to be a 24-channel spatial domain image. However, we're going to pass this spatial domain image through a Fourier transform and end up with the K-space image with 24 channels. Those 2 outputs of the K and I modules are going to be concatenated into one single image of 24 channels. The second block is similar to the first one. However, the output of the first module, this means the output of the K module, is going to pass through an inverse Fourier transform. So here, instead of the K-space image, we're going to have the spatial domain image. And instead of passing the output of the I module through an FFT, you're just going to use the spatial domain image that is outputted by the I module. So in the second block, our output is going to be an spatial domain image of 24 channels. In the second step of our architecture, the module is going to use the output of the first block as input. So the first block of the second step has a chi-space module. So its input is going to be a 24 channel chi-space image, and its output also is going to be a chi-space image that is going through an inverse Fourier transform, and we're going to end up with the spatial domain image of 24 channels. The second block of the second step of the network is an image block, so it processes the spatial domain image. It has as input and output the spatial domain image of 24 channels, and its input is going to be the output of the second block of the first step of the network. Finally, we have the last step of the network, which is an image module. So it has as input an image of spatial domain of 24 channels, and as output an image of spatial domain also of 24 channels. The highlighted boxes here are concat and conv layers. They are meant to concatenate the output of two parallel blocks into one 48 image output. This 48 image output is going to pass through a 3x3 convolution, and the output is going to be a 24 channel output. Our architecture is composed by three main steps. The first one produces the first convolutional reconstruction. However, those reconstructions are weak. This means that they do not have a good quality. This first step is composed by two blocks, as I said before. And despite they are pretty much similar at the beginning, they are K and I modules with the same inputs and the same outputs. We actually have different objectives for each module. So the main objective of the first module is to learn chi-space parameters, and the main objective of the second module is to learn the spatial domain parameters. And at the end of each module, we have the concatenation and convolution for the final image of this step. The second step refines the results of the first two parallel blocks. So here we already have a better resolution image. At the end of the second step, we also have concatenation and convolutional layer. Finally, the third step is to fine-tuning the reconstruction results. It's important to highlight here that all the modules are trained together. So we train the whole architecture at once. In our experiments, we have as input for the K modules the 24 channels K-space sample data, and for the I modules the 24 channel image or spatial domain generated by the inverse Fourier transform of this sampled K-space. Our optimizer was the Atom. The data mutation used was actually in the R sampling, so our R masks were random. This was our data mutation. Our loss function was the mean square error, and at first we had an initial learning rate at 0.01, and then when our training started to diverge, we changed it to 0.001. Here you can see the preliminary quantitative results of our method for both R equal 5 and R equal 10. You can see that using R equal 5, we get better results than using the R equal 10. Here we can see some visual results. We can see clearly that the r equals 5 returns us better results than the r equals 10. This can be also analyzed by checking only a patch of the image. We can see that using the acceleration factor of 5, we can see some shapes and borders in the image. However, with the acceleration factor of 10, we can only see a blurred image. So, as conclusion, we can say that a single unit is not sufficient to produce a high-quality reconstruction image. Our method is introducing the parallel analysis of k-space and spatial domain images together and combine those methods. One possible approach to improve our results is to pre-train each individual unit as a single module. As I said, we train all the architecture at once. So we could just train each module individually and then use the final training weights of each single module on the parallel cascade module. And finally, the concatenation block between the modules could be more explored. If we change the order of the concatenation and convolutional hyperparameters, this could also improve our results. Thank you very much.
Thank you for the presentation, guys. We have time for a few questions. I can start. So you talk about 24 channels. So I guess you're treating the 12 channel data and you're splitting real and imaginary, and that's why you talk a lot about 24 channels. Is that correct?
Yes, correct.
Also, I'd like to congratulate you guys. I think there are many techniques for MR reconstruction that are based on cascading networks. I think the first one was published in 2017, and they are actually really good. And I think it's sort of a trend. People are starting to investigate to have those parallel models in which you have many different models in parallel on different domains and different cost functions. I'm not sure I understand. So you have two parallel branches at the beginning. They are the same, but you said they have different objective functions. Is that it?
No, actually, their final objective is different. The first branch has the objective of output a spatial domain image. So they need to learn their weights need to be learned based on the spatial domain image as output. The second one needs to be learned based on the k-space domain image. So even if the inputs of the parallel blocks are the same, they are not going to be the same weights for the two different blocks because their final outputs are different. So they, what I say is objective here is what each block is trying to learn actually.
Okay, so what's the overall cost function that you guys use to train your model?
The mean square error.
Thank you. Does anyone else have any question to the ML Unicamp team?
So you're learning a unit directly on k-space data in addition to the image data, right? So, so what's the rationale behind it? And did you see an improvement over just learning in image space in your experiments?
Sorry, I didn't get the beginning of your question. Could you please repeat the beginning?
Oh, sorry. Yes. So you're training a unit both on the image domain data and on the k-space. Is that correct?
Okay. Actually, we are training both of them. We're training in k-space and in the image or spatial domain. So sometimes in our module, we have to perform Fourier transform or inverse Fourier transform, depending on what is going to be the next step of the module. if I was clear.
Okay, yeah, thank you.
So I'm gonna share my experience. Maybe it relates to the question just asked. So usually when I'm dealing with multi-channel data all at the same time, I've seen some advantages to training both K-space and image domain. But when you have just one channel or you combine all the channels before training the model, usually it seems that image domain gives better results. That's just some experimental results that I had. And I see there's a question in the chat.
That's my question. So, but now you mentioned this, that in multi-coil, it does make sense. So maybe that's a kind of, because coil sensitivity estimates, as I also discussed this with Matan, so coil sensitivity estimates are multiplications in image space, so kind of convolutions in K-space. So you could imagine that maybe that way it's kind of estimates that. But otherwise, to me, it sounds weird to do convolution in K-space, since K-space is global data and convolutions are local operations. But maybe it works, but it eludes me why.
I think you're correct, but like I think they process the channels, all channels at the same time, and there are correlations across those channels. So I think the idea is similar to parallel imaging GRAPPA, in which they use convolutions to estimate the missing K-space points. But yeah, we can discuss that more at the end of the session. Now let's move on to the final presentation. And the final team is Resonance with a double N. So it's your team, Jonas. If you guys want to present yourselves prior to the video presentation, that would be nice. Thank you.
Yes, I'll kick off. So we started with developing this, the recurrent inference machine in, I think, 2016. So it's published now in Medical Image Analysis 2019. We also participated in the Fast MRI Challenge. We're now teaming up with the four of us. And one thing to mention also is the contribution from mainly Jonas in setting up the code base. I mean, according to the guidelines of the challenge, this is now available through his GitHub, but the link will appear in the presentation later on. So far for my introduction.
Also, we're from the Netherlands Cancer Institute and the Amsterdam Medical Center, right?
Yes.
Yes.
Okay, does anyone else in that team want to introduce themselves? I see Dimitrios is here. And
yes, hi, but I think I will introduce myself in the presentation, so I guess you can start.
okay, so I'll start the presentation. Thank you. So this is the final presentation before we go to the results session.
Hello everyone, my name is Dimitrios Karkalousos and I'm going to present you our work of applying the recurrent inference machine to the multi-channel MR image reconstruction challenge. In no particular order, this is our team with Jonas Teva, Nikita Moryakov and Matan Khan. Let's start by introducing the forward model of MRI reconstruction. We have a fully sampled image X, and by taking the Fourier transform, get the K-space measurement, and after applying a sampling mask P, we get sparsely sampled K-space measurement denoted by Y. Then, through the inverse Fourier transform and by taking the sum of squares, we get the zero fit reconstruction. And taking into consideration that we have applied the sensitivity maps denoted by capital S for total number of coils C. Then we can formulate the forward model such as Y is equal to the Fourier transform of the fully sampled image after applying the sampling mask P and the sensitivity maps, where H is the adjoint operator, plus N, which is white noise produced by the scanner for total number of coils C. And this is our prior knowledge. This is our knowledge of how an MR image should look like. And the goal is to find the inverse transformation of going from the partially sampled K space to the high resolution image. This inverse transform can be found through the maximum a posteriori estimator, where we are trying to maximize the probability of our estimation looking like the fully sampled image. The log likelihood is derived from the forward model given by the error between our reconstruction and the acquired measurements. In order to solve this inverse problem, to find the transform, we use the recurrent difference machines, which were introduced by Patrick Putsky and Max Welling as general inverse problem solvers, and Kai Luning has published a paper using the RAM to reconstruct heterogeneous MRI data. By having the forward model implemented, by having the physics explicitly implemented, the RAM is trying to solve the inverse problem of accelerated MRI reconstruction over multiple time steps denoted by capital T. So let's try to get a better intuition of how we're doing this. Let's try to unroll the RAM over multiple time steps. Here you see the model on this box denoted by H-phi. The network has two states. The external state denoted by X, which is initialized to the inverse Fourier transform of the subsampled K space, and a hidden state denoted by S, and at this point please don't confuse this with the sensitivities map, which we initialize to 0. And the prior is learned implicitly, since the physics are explicitly modeled. Those two states are given as input to the model, together with the log likelihood gradient, which will guide the network's gradients to the right direction to learn how to estimate the fully resolution image by calculating the error between the estimation and the initial measurement. At the next hidden states, the network will be updated by a function denoted by G here, which has a notion of memory and can discard information that seems to be unuseful and keep only the useful one. And the next external state will be updated with learned parameters and produce a better estimation. Then we calculate again the log likelihood gradient, and we give them as input to the model together with the previous hidden state, and we do that over multiple time steps, where the total number of time steps is denoted by capital T, and tau is the current time step. Here you can see the architecture of the model, which combines a sequence of convolutional and recurrent layers, and here we use gated recurrent units. And as mentioned before, we give inputs to the model, and the model will be able to update its hidden states with better estimations of the MR image, and the output of the model is summed with the previous external state, and results in better estimations over the time steps. So next I would like to explain you how we did the coil sensitivity estimation, and to do that we extracted the auto calibration signal region as a mask, and we zero out all the lines except the signal, which will result in a mask as the image you see on the left. Then we apply this mask to the K space, and we take the inverse Fourier transform, which will result in an estimation denoted by X hat. And finally, we normalize this estimation by the root sum of squares. And this will result in a coil sensitivity map as the one you see on the image on the right. So we had the multi-channel MRI reconstruction challenge, which gave a dataset consisting of 167 3D T1 weighted scans of 12 and 32 channel coil images, which on the in the Z direction, only 85% of the K-space data was collected, and the remainder were zero field. For evaluation, we had the SSIM, the PSNR, and the visual information fidelity. And for sampling masks, we had sampled from Poisson distribution with acceleration factors of 5 and 10 times. So what we did for the challenge were to fine-tune our models, and as far as for data, we cropped the K-space to arrive at data of same size, ignoring the aspect ratio variation, and we did zero filling for partial free acquisition. To select the best model, we trained several models on both acceleration factors, and we compared on two systems for achieving the best performance. And for the loss function, we tried several options, and we selected the SIM plus the L1 as the best option. And for the network architecture, we selected 128 heated channels, 16 time steps, and a depth of 2, which resulted in a model with total number of parameters around roughly 360,000. So here are the results used on the validation set for the 12 channels. And you see, as we're going through the slices, one volume, the SSIM doesn't drop significantly in performance and can maintain the robustness for both acceleration factors, but of course drops in performance for 10 times acceleration. And I would like to show you this image where for the reconstruction on the 10 times accelerated, on the right you can see some spatial distortions and a hallucination of a cortical white matter, great matter in the cerebellum, and assume that the intensity of the bias field is having some impact here. But you can also appreciate that for the 5 times accelerated image, the image on the middle, it preserves the spatial detail and results in reconstruction close to the fully sampled target image. And finally, we have some pre-submission results comparing to the zero field reconstructions, although it's not a fair result comparison because the results for the zero field reconstruction are from the whole test set, and the results for the RIM are from a subset of the test set. Although you can see that the model performs fairly well for 5 times acceleration and also well for 10 times acceleration on the 32 coil images, but drops significantly in performance for 10 times acceleration on the 12 channel coil images. But you can also appreciate here that as you see on the images on the right, for both 12 and 32 channels, it can preserve the image contrast and results in reconstructions close to the target image, although for 10 times acceleration we have a bit more blurred results. So finally, I would like to thank the funding source of my PhD program and our team with Jonas, Nikita, and Matan. And I would like also to mention the Deep Image Reconstruction Toolkit, which is our try for open source coding. We have implemented the recurrent inference machine, which was also part of the winning solution in the Fast MRI challenge. And in this repository, you can find the implementations for both challenges. And if you have any questions or any ideas, please feel free to contact us. Thank you very much.
Thank you for the presentation, Dimitrios. Is there any questions? First, I would like to congratulate the team. So they won the Fast MRI challenge. Was it both tracks, or the single channel, or the multi-channel track?
So it was for the single coil.
So you guys are the defending champions. One thing that I noticed during the presentation, you have one of the smallest models that we've seen so far, only 300,000 parameters, but still the training time seems a little bit long, 2 to 5 days. Can you comment about that?
I can comment on that. It's a recurrent model, so that it's much slower to train than a CNN type model. And another thing, than a standard feed-forward model. Another thing is that we only trained like one model for quite a long time, so there was no we didn't have the time to select better hyperparameters to perhaps see it train faster. Yeah, so it could be improved, but inference is super fast, so that's one thing.
So maybe Jonas, you can also comment on the resources to train on.
Yeah, we did have quite some significant resources. We have this RTX 8000 to have 48 gigabytes of GPU memory. And I see there is a question on a number of iterations. I think we took like 500,000 iterations. So an iteration is one batch. And with this machine, we could have, I think, a batch size of 8 or so. So there would be 4 million iterations. Yeah. So, but one thing to mention, so we did train for quite some time, right? We just wanted to see how it converges, and you see that the loss curve flattens out, but we still let it train a bit, because often you can see that if you do this after the loss flattens, that the generalization properties are better. The metrics might not improve, but the generalization properties often improve. So that's why we let it train for longer than what is likely necessary to do to get good results.
And one property of the recurrence of the network is that it has like implicit increased depth compared to other models.
Thank you. I have a couple more questions. The second one, how did you design the loss function you guys use?
I can comment on that. So first of all, we looked at the metrics that were relevant. So that's PSNR, visual information fidelity, and SSIM. So you know that PSNR is kind of very related to L2. So if you could optimize L2 if you want to optimize L1. There is this other paper that does stuff like high resolution with convolutional neural networks, which actually shows that for high resolution, sometimes it's better to use L1 loss rather than the L2 loss. And you can often see that even when you train on the L1, the L2 loss will be lower than when you would have trained in L2. So that's so we used an L1. On the other hand, we also use structural similarity. We also saw this in the Fast MRI challenge. All the winning solutions had structural similarity as an additional loss function. And this is also what we saw in quick experiments. If you only do L1, you get a very good PSNR, but you don't get a good structural similarity. So we added this. And we didn't have a differentiable visual information yet. We didn't have a good feeling for this yet, because we did do this in a Fast MRI and not here. So that's why we stick to.
Thank you. There are a couple more questions in the chat. The first one is about reading multi-channel data and sensitivity maps from memory takes a lot of time. How did you overcome that while training?
So we didn't read any sensitivity maps. So we just estimate the sensitivity maps by masking out. We take the k-space and we only take the auto-calibration signal, so the circle in the center, to compute an approximation to the sensitivity map, and we put this into the log likelihood gradient. So that's almost cheap for free. This is a CPU computation, so it shouldn't slow that much down. On the other hand, this H5 format, it's a memory mapped format, so it's pretty simple to just read in slices. So we did a 2D model. If you look at the results of our 10x model, we could expect that 3D models would actually also improve, but we didn't try that. So reading single slices in an H5 file should be super fast. We didn't have any I/O bottlenecks, so you can check out the code we have. It's on GitHub. That's also the code that we used to build the model with. There is no, I mean, we don't notice any I/O bottleneck with these things. But I should mention we put it on an SSD, but I don't expect that on a spinning hard drive, reading from H5 files would be that slow.
Thank you. Just one final question. Did you guys try using the model you trained for the fast MRI to predict the images in this challenge, or the other way around, the models you caused this challenge and you predicted on the fast MRI?
No, I didn't. I mean, I just wrote the whole code from scratch because we wanted to have a kind of a nice framework for our future research, and this challenge came along and it was a nice thing to try. So we basically wrote the whole code for that. I would have to look into my previous stuff to know if that actually would work. But I would expect it. So there was some change. It was different in the fast MRI challenge because we mainly participated in a single coil because we didn't have that much compute yet. You also do the multi-coil challenge, and in those days we didn't do much with the coil sensitivity estimation either. So I'm not sure if that would actually be a good try. Here I noticed if you don't do coil sensitivity estimation, that the results are bad for these models.
I think there's one final question in the chat.
Yeah, the background noise. So there's a problem, but yeah, you can fix that. I mean, in the log likelihood gradient, when you look at the inverse problem and you derive the log likelihood gradient, you do end up with the sigma of the k-space noise, or the Gaussian noise in the complex data. We tried to estimate that before. It's tricky, but one thing you should know that since the ground truth is the RSS, so if you really would reduce the noise in the background, we might get better images, but we get worse metrics. So we didn't do that on purpose.
Yes, that last comment that you just made, I think we're gonna see that during the results section about filtering background noise or not. And thank you for the presentation. So I guess this is the moment that everyone was expecting. So we're gonna go to the results of the challenge. I want to remind you that the baseline models, they are there, but they are not used to define who wins the challenge, who is first, who is second, or who is third. Okay. Oh, sorry. Sorry, there we go, the results of the challenge. So the first track, right away. So acceleration of 5 using 12 channel data. So those are the results. In red, we have the best metric. In yellow, the second best metric, and in green, the third best metric. Resonance was the best team in 2 out of the 3 metrics in this case here, both structural similarity and peak SNR. Feel free to comment during the presentation. So if you have any questions, just unmute your microphone and ask a question. So we can see here peak SNR of 34.4, a high structural similarity of 92, and a VIF of 93. Here we have some sample reconstructions for the different models. I would say all models except for zero field reconstruction and the UNet, they give you, well, they seem to give you nice reconstructions. If you look here in the GIF and the resonance, you can see a little bit of the noise as well as in the ground truth. I think that was the comment that Jonas was making before, while in the other submissions, it's mostly black. I think we lose the noise pattern in the background, which potentially gives you a better image, but hurts your metrics, like you mentioned. Just a single shot of the results. So you can see here this area. Resonance is able to get a nice reconstruction there. Zero field and UNet, you practically lose the information. And the other techniques, they can recover a little bit, but some of the information is lost. Moving on for the acceleration of 10. Here, resonance was #1 for all the metrics. And second and third place were sort of split around different models, but they were all very much similar, I would say. Here we have another sample reconstruction for an acceleration of 10. You can clearly see that resonance is the one that is closest to the reference. You still have a lot of the fine details in the image. Obviously, you lose some information, but compared to the others, the reconstruction seems to be a little bit superior. So for the first track, the ranking here is on the right. So resonance was #1, ML Unicamp #2, and TU-MRI was #3. Here's the overall results if you consider all the models, all the baseline models as well. Congratulations, Resonance. You guys are on top again. All the other models, TU-MRI and ML Unicamp, they had good reconstructions. We could see in the images. I guess they didn't have much time to fine-tune their models as well. They were working using the Amazon computers. So it would be nice to see in the future whether they can fine-tune the models and how much they can improve the results. For the second track, Resonance was the only team that submitted, and we have fewer baselines here. So you can look at the metrics for an acceleration of 5 and using 12 channel. For an acceleration of 10 and using 12 channel. I'm not showing the images again because Resonance has a model that is independent of number of channels, so they would be the same images that I showed before. And here for the 32 channel. One thing that it's interesting to note is that for the 32 channel, and the metrics still look pretty good, but when you go to the images, and they don't look so good anymore. So here for acceleration of 5, we have 2 examples. Resonance is here. So for an acceleration of 5, it looks a good reconstruction. We receive some artifacts. Yeah, you can see some artifacts on the reconstructed images, but it's hard to make a model that will generalize to an unseen data set. So the reconstructions look pretty good. For an acceleration of 10, metrics are a little bit lower, but they look like good numbers. But when you go to the images, and that's what we got, you can see some artifacts. sorry, that's actually R equal 10 here. But you can see that the artifacts are more evident on those images for an acceleration of 10. They were the only team that submitted, so they were #1 as well in the second track of the challenge. And those are the results. Hopefully we can discuss them a little bit. Does anyone have any comments, or does
I
anyone
was just wondering why the artifacts showed up most at the top and the bottom of the image, not so much in the middle? Is it because the signal is so much higher from the front?
So I'm just showing one example here, but there are images, there are cases in which the artifacts appear in the middle as well.
So
Is it
we
related
saw
to the
actually,
flat signal, or is there some correlation with that, or is it somewhat a random effect throughout the slices?
I don't know, maybe the resonance team has an answer or an hypothesis for why that's happening with the reconstruction.
well, the thing I wanted to say is that we saw the blurring mostly in the center of field of view. And we think that's to do with the lower signal there, so or the higher noise, so you get easier get blurring of the data. But the striping is new to me, at least. I would have no answer to that actually.
So I just published the results to the website. So if you guys want to see with more detail and the metrics, it's available now on the challenge website. So one question, how difficult was to adapt your models to the challenge data set? Can any of the teams share their experience?
Yeah. Can I? So when I developed the code, I wanted to make sure that it works kind of out of the box for the fast MRI and the Calgary-Campinas dataset. And the only difference that we needed to, the only thing I made was an H5 slice base class, and then some small changes between those two datasets. So the fast MRI dataset stores it in complex floats, and here it's 2 channels. So I put in some conversions there. I think it's only took 50 lines or so to adapt from fast MRI to this.
Other things we discussed is the zero filling of the data we chose to ignore, and then the cropping. This is I think what Dimitri's presented as well. So we crop the data to standardized sizes, and we ignore the effect it had on the aspect ratio. So that's a small consideration.
How about the other teams? How hard was it to get the data set, train a model, and make it work?
Actually, for us, our main difficulty was in choosing the library we were going to work with. At first, we were working with PyTorch, but we had some difficulty in working with complex data in PyTorch. So our model was not converging because of this. So when we moved to Keras, then it was things start to flow better. But this was our main problem here with the data and everything. But about the model, actually after we changed to Keras, our model just started to converge better, so things were flow better, as I said.
How about you, Mike? How hard was it to get the data set and adapt your model to use complex numbers and make it work and converge?
The integration of the dataset was not too hard. We also used the data loader of fast MRI and just had to do some slight small modifications. And then it worked. We had one rather stupid mistake. We applied the mask invertedly for like until 10 days before the challenge. So we actually sampled from the image everything that should have been discarded. And when we then tried it on the test data set, we got very blurry results. And after some exploration, we found out what happened, and so we had to change it, but in the end, it didn't change too much. And another thing we had was the use of the width loss. So our width loss function inherently normalizes the data range, I think, because it is pretty constant, no matter whether the ground truth is in a totally different data range than our training or the output of our neural net. But with metric that is provided by Skype or I don't know, from the library, doesn't do that. And so when we only had the width loss function and now L1 integrated, then the output of our neural network was in a entirely different data range. And so the width metric was 0.01 or something, even though to the human eye it was a very, very good reconstruction. And the other two metrics were still very good, so SSIM and PSNR. They don't care about the data range. I think they normalize it as well. But so this was a problem, and then to get to the same data range, we decided to do this weighted L1 in there, and then it actually worked.
Thank you. So one question. So based on the results we saw on the 32 channels, so they were good results, but do you guys have any ideas on how to make models generalize better across data sets? Any suggestions, any comments?
Yes, I think we need to use less parameters and simulate different sensitivity profiles. So since we have the full we have the full data, the 12 channel data, we could have simulated a 32 coil version or 24 coil version or whatever. We can just simulate sensitivity maps based on the complex reconstruction. I think that's would be one way to go, and have less parameters.
One question for all the teams. Did you guys use data augmentation, but in the traditional sense of making rotations, translations, and scaling of the images?
Yeah, we dropped. There was also a bit of a pragmatic thing, because you want to do batch the data and they had different sizes. So we did some random cropping to make them the same size.
We didn't apply any auto augmentation yet.
So we decided to use this metric called VIF, Visual Information Fidelity, and based on a paper that was published last year at IEEE Transactions on Medical Imaging. So in the paper, they show some results that the metric better correlates with the radiologist's opinion. I contacted the authors and asked them how they use the metric, which kind of normalization, which noise level they use to compute the metrics, and we tried to replicate that. But what was your overall impression of VIF as a metric for MR reconstruction? I must say that I'm still not sure whether that's a good metric or not. If I'm not mistaken, MIDL had some issues with the metric at the beginning.
Yes. Yeah, as I said, it was the thing of the data range. So as far as we understand it, the metric is very sensitive to normalization. So if you normalize the image differently, to the human eye, it will still look the same, but the width score can, at least in this implementation, can differ between 0.001 and 150. So I once had a width score of more than 5,000, which of course makes no sense, but this is somehow caused by the normalization. So if the ground truth and the reference are the reconstructed image and the reference are in entirely different data ranges. And when we zero center it, then we can circumvent that problem.
Thank you, Mike. So what do you guys think is the maximum acceleration we can achieve for those images, T1 weighted brain images? And since we're working with 3D data sets, you can undersample in two directions. I guess the fast MRI is a 2D data set, so you can only undersample in one direction. They use an acceleration of 4 and 8. And we have 3D data, so we thought that maybe the data is more sparse, and we're using an acceleration of 5 and 10. And do you guys have an opinion about by how much we can accelerate MR scans?
So, yeah, so if I may start based on our results, the answer would be in between. So somewhere in between 5 and 10. So the 10x data were a bit blurred in certain ROIs, as you already pointed to. So that's pushing with the current implementation. So then 7 or 8x should be feasible. But that needs to be proven, obviously.
Yeah, so in this data set, so K-space is partially collected in the slicing code direction. So if we compare how much we sampled compared to the overall K-space, the acceleration will be actually close to 6 and 12 for each track. Obviously, I compute the acceleration based on how much was sampled. But if we compare against what would be the fully sampled image, the acceleration factors that we are using in this challenge is close to 6 and close to 12 times. Does anyone have any comments? So we have a small reward for all the teams that participated. We're going to announce in the next session. Yusuf is going to present some potential future directions for this work. And then you guys are going to receive the reward on your email boxes pretty soon. So I'm going to play one last video.
My name is Yusuf Boufaris, and I will be presenting on the work our team has done to further improve deep learning-based magnetic resonance image reconstruction beyond the scope of this challenge. Our medical image is processed and interpreted only to be set aside. They should be continually revisited to guide decisions around future episodes of care. However, that is currently not the standard for image acquisition and reconstruction. Therefore, we need to think of better ways to integrate this abundance of data to optimize this process. Patients with ongoing medical conditions often undergo several scans throughout their lifetime. Can these previous scans be used to enhance the reconstruction quality of a patient's follow-up scans? The steps to achieve this in practice would be as so. A patient would come in for their first scan, where they would undergo a traditional acquisition and reconstruction. Upon their second visit, they would be eligible for an accelerated acquisition, from which an initial reconstruction is produced, which is then coupled with the previous scan to leverage the mutual information contained to achieve an enhanced reconstruction, which ideally resembles the quality of a fully sampled reconstruction obtained at a fraction of the time. To achieve our goal of repurposing previous subject scans, we propose a modular processing model. Undersampled K-space measurements are input into a reconstruction network. In this case, we used WWNet IKIK. However, any similar model such as those proposed in this challenge could be used to obtain the initial reconstruction. Next, the previous scan is registered to the initial reconstruction using linear registration. The registered previous scan and the initial reconstruction are then input into the enhancement network, consisting of a single unit to obtain an enhanced reconstruction. The modular nature of this processing model allows us to modify and improve each step easily and independently of one another. The enhancement network consists of a residual unit. There are two inputs, the initial reconstruction and the previous exam co-registered. The unit would then output the enhanced reconstruction, and the mean absolute error is used as the loss function. The data used in this study came from presumed healthy subjects with an average age of 45 years. The initial reconstruction network was trained using the same dataset from this challenge. The enhancement network was trained using 21 pairs of longitudinal scans. It was then tested on 18 separate pairs of subjects. The average time between scans was 4 years. Models were trained for each of the acceleration factors, 5, 10, 15, and 20. In this study, we anticipate some natural changes to the brain structure due to aging. The longitudinal correlation decreases as time goes on. This is an observation we must be aware of when trying to use the previous scans to enhance the reconstruction of their following scans. 3 traditionally used metrics were used to assess the quality of the reconstruction when compared to the fully sampled reference. The first is structural similarity index, the second normalized root mean squared error, and the last is peak signal to noise ratio. These metrics were used to assess and compare the quality of the non-enhanced and enhanced reconstructions obtained from the initial and enhancement networks respectively. The average metrics were computed for all 13 subjects at each acceleration factor. Statistically significant improvements were recorded across all scans. The average structural similarity increased by 16.9%, peak signal to noise ratio increased by 8%, and the normalized root mean squared error reduced by 22.7%. The benefits of this methodology are most clear when comparing the results of the enhanced reconstruction for an acceleration factor of 20 and the non-enhanced factor of 10. With half the data, the enhanced reconstruction offers comparable results. The enhanced reconstruction is sharper and clearer than its non-enhanced counterpart, which does not leverage information contained in previous scans. Blurring artifacts and residual maps are also significantly reduced after enhancement. This observation is most clear for acceleration factors greater than 10. FreeSurfer software was used to perform volumetric analysis on both the enhanced and non-enhanced reconstructions for all acceleration factors. The absolute error when compared to the fully sampled reconstruction were plotted for the brain volume, white matter volume, gray matter volume, and for all acceleration factors and measurements. Statistically significant improvements were reported when comparing the initial reconstruction to the enhanced reconstruction. FreeSurfer segmentation masks were computed for the non-enhanced and enhanced reconstructions. What we see is that the enhanced reconstruction in the highlighted region has more refined structures and details comparable to the reference than its non-enhanced. A major concern surrounding this approach is the potential for the previous scan to incorrectly bias the follow-up scan after enhancement. In this figure, we highlight a region of the brain that appears to have changed between the previous and follow-up scan. This is likely due to the use of different acquisition parameters. This region of the brain appears to be lighter in the previous scan and darker in the subsequent scan. However, the enhanced reconstruction was able to adequately reconstruct this region of the brain, resembling the fully sampled reference. This is likely due to the fact that the initial non-enhanced scan serves as a very accurate starting point for the enhancement network. Although this example appears to be successful, we still do not know the full effects that the previous scan will have on the enhanced reconstruction. Therefore, more testing has to be done to fully define this relationship. This project was to test this methodology on a group of patients with evolving diseases, such as brain cancer subjects. Preliminary work was done to compare the results of using linear registration versus nonlinear registration. As we can see both visually and from the correlation plot, there is a notable improvement when using nonlinear methods. Teams that have submitted to the challenge will receive early access to the longitudinal data just described. So please check your mailboxes. Thanks to all who listened, and a special thanks to those who participated in this.
Thank you. So this final presentation is one possibility for a continuation of this challenge. So there are many people investigating reconstruction. Other groups are looking into reconstructing several sequences at the same time. And we are also trying to incorporate longitudinal information from previous scans to see whether that prior can improve reconstruction of follow-up scans. You guys probably have just received the email with the link for the data set. Feel free to use it any way you want. I guess that concludes the session today, the challenge session today, but I'll be available, the team will be available for any questions that you have. And if you have further points to discuss, please unmute your microphones and just ask your questions. Thank you.
I don't have a question, but I want to thank you for the organization. The generalization to multicoil is very interesting. It's definitely something we want to explore further.
I must also mention that we have some 32-channel data sets that were not included in the challenge. So if you guys are interested in getting those data sets to see if you can improve your model to 32-channel, maybe train using both 12-channel and a few data sets for 32-channel, and just let us know. That I think we can probably share that data set.
Oh, that would be amazing, yes. That would be cool. Thank you.
And I'd just like to stress again the value of the data set that you acquired, Roberto. And we had contact about that before, and for us now, we're facing some challenges to acquire brain data and to be able to share this, which will be an active point of research for us as well. So it cannot be underestimated, the value of the data set that you are sharing now with the world.
Thank you. The credit here goes to my previous supervisor, Richard. He allowed me to share the data set. So I always ask my supervisors, can I make this public? And he actually allowed me pretty much every time that I asked to make a data public. He allowed me to make that data set public. So thanks to Richard as well.
Hello everyone. Hello. I have a question for team resonance. So you are using sensitivity maps to combine the 12 channels into two. Are you making them into 2 channels and giving it to the model? So, and the model is taking only 2 channels. So the model, so it won't be a matter for the model whether it is taking 12 channels or 32 channels. So what could be the reason for the artifacts that we are seeing in the results of 32 channels?
There was some background noise. I'm not sure. Could you guys hear the question? I think it was directed to the resonance team.
I vaguely understood it, but I didn't. I thought maybe Matan understood better what I said, so that's why I didn't reply yet. Could somebody paraphrase the question?
Can you repeat the question?
Sure.
Thank you.
Yeah, sure. Actually, first of all, congratulations to Team Resonance. My question is, you are using sensitivity maps to combine all the 12 channels, and those 12 channels you are making into 2 channels and giving it to the model. So the model is taking only 2 channels. So when you are evaluating on the 32 channels, what can be the reason for those artifacts? Because model should not be a matter for the model whether it is taking 12 channels or 32 channels.
Yes, that's true. Yeah, we do want to improve the choroidal sensitivity estimation. So now it's just very brutally just try to reconstruct on the ACS and then do a very rough estimation, but we do want to improve it by using a model as well in that part. But maybe that doesn't help the generalization to 32 coils. So then we would likely need to also do kind of augmentations on the sensitivity maps. I think we can do this. We can reconstruct images to complex valued, and then simulate new sensitivity maps, which could be reasonable for such problems. I think we can solve this with augmentations.
Oh, thank you.
Still, it would be good to understand why these horizontal striping patterns appear, right? So maybe we can inspect the sort of the dynamically this reconstruction, or do an IFFT, see if there are any spikes introduced in K-space. I have no idea.
Yeah, I think in the reference we can see some spikes, some artifacts, and it seems that the reconstruction model amplifies those artifacts, if that makes sense.
Okay, we didn't check this. This is also the case in the fast MRI. You had a spike noise, and it helps to remove it. So we didn't do any of these checks on this data. So maybe that would be a solution.
Yeah, I would also like to add, if any of the teams, they require further metrics, and we are available to compute more metrics in the submission. So if you feel there are more metrics that are important to better understand the results, we would gladly compute those metrics for you. And if you want also further images from the test set, reconstructed images and the fully sampled images, let's say for a paper or something, we are also available. Just write us an email and ask what you guys need for your work. And also in the future, we only had 3 submissions and just 1 submission for the second track. So hopefully when we get more submissions, we'll try to make a combined publication comparing different reconstruction techniques in the future. But I'm gonna give a little bit more time to the community so we can get more submissions.
Yeah, we'll do our best to announce this event, and hopefully this will raise more awareness.
Thank you, I appreciate that. Any more questions?
So if I may add, I would like also to thank you and everyone for organizing the challenge. It was really nice, and I would also like to point out one more time for the sensitivity maps that is important because it's part of how the forward model is formulated. So if we don't have good estimations of the sensitivity maps, we won't be able to have good reconstructions in the end. So it makes sense from the first step. And also to add for the previous question, for the fast MRI challenge, we were top on the single coil. So basically we didn't use sensitivity maps. And for the multi-coil, we just used different channels for the models. So for this challenge, it wasn't really applicable to use the larger model we used there because we used a different approach to formulate the forward model. Thank you.
Thank you. Any more questions? I guess you guys received the email with the link to access the data, the longitudinal data. Okay, if there are no further questions, I'm going to conclude the challenge session. And thank you very much for being present today, for your submissions, for the emails and the feedback on the challenge. That is highly appreciated. I hope we can keep in touch and maybe collaborate in the future. People in Europe, please have a good night today. People in Brazil, enjoy the rest of your afternoon. People in Canada as well. I appreciate the people that are not involved in the challenge, but also came here to the session today to participate. So thank you very much for everything. Stay safe. Bye-bye, guys. I'm gonna end the session.